I have three scientists standing before me. One says an acid must produce hydrogen ion in water. The second interrupts and says, no, that's not the whole story. Acid simply donates proton. Before you can decide who is right, the third scientist smiles and says, both of you are still thinking narrowly. Some acid-based reactions don't involve protons at all. Wait, no proton, no hydrogen, still an acid-based reaction. That sounds impossible, but by the end of this lesson, you will understand why chemistry textbooks contain three different acid-based theories, why scientists kept changing the definition of acid and bases, and which theory is considered the most powerful today. Let's begin. Welcome back, hello everyone, to this channel. If you are preparing for any of the exams, whether WAEC, NECO, JAMB, IJMB, JUPEB, or you are studying chemistry at the university, this lesson will strengthen one of the most important foundations in chemical science. Today, we are comparing the three great acid-based theory. Number one, Arrhenius Theory, Brønsted-Lowry Theory, Lewis Theory. But instead of memorizing definitions, we are going to understand why each theory was developed and how chemistry evolved over time. Imagine you are a scientist living in the late 1800s. Chemists already knew substances like hydrochloric acid, sulfuric acid, and sodium hydroxide. They observed predictable reactions. Acid reacted with bases, neutralization occurred, salt formed, but there was one big question: what exactly makes something acid? No one had a complete answer. Then came a Swedish scientist named Svante Arrhenius in 1887. He proposed a revolutionary idea. He said, when an acid dissolves in water, it releases hydrogen ions. Similarly, a base releases hydroxide ions. For the first time, scientists had a practical definition. It worked beautifully until chemistry became more advanced. The Arrhenius theory is the simplest of the three. According to Arrhenius, an acid produces hydrogen ions, or more accurately, hydronium ions in water. For example, HCl dissolves in water, it transfers its proton to water, producing H3O+ and chloride ions. The presence of H3O+ is responsible for the acidic property of the solution. Now look at sodium hydroxide. Sodium hydroxide dissociates into sodium ions and hydroxide ions. The hydroxide ions gives the solution its basic character. So the Arrhenius definition are: an acid increases the concentration of H3O+ in water. The base increases the concentration of OH- in water. Very simple, very useful, but there was a problem. What happens if there is no water? Consider this reaction: Na3 gas plus HCl gas to give NH4Cl solid. No water, no solution, yet a clear acid-base reaction occurs. According to Arrhenius, this reaction shouldn't even fit the definition. Scientists realized that the theory was too limited. They needed something broader. Then in 1923, two scientists working independently, Johannes Brønsted and Thomas Lowry, introduced a completely new perspective. They shifted the focus away from water. Instead, they focused on movement of one tiny particle, and that particle is proton. Their definitions became beautifully simple. An acid is a proton donor, a base is a proton acceptor. Watch the proton in our earlier reaction. The hydrogen chloride gives away H+. Ammonia accepts it. Immediately, NH4+ forms. This explains reactions occurring in water, without water, in gas, and in many non-aqueous systems. It solved the weakness of Arrhenius. But chemistry wasn't finished evolving. Scientists encountered another type of reaction, one that looked like an acid-based reaction. Yet, there was no proton anywhere. Imagine this reaction: BF3 plus Na3 to give BF3 connecting to Na3. Where is the hydrogen? Where is the H+? There isn't one. So how can this possibly be an acid-based reaction? That same year, 1923, Gilbert Newton Lewis proposed the broadest acid-based theory ever developed. Instead of following protons, he followed electrons. A Lewis acid accepts an electron pair. A Lewis base donates an electron pair. Now look carefully at ammonia. Nitrogen possesses a lone pair of electrons. Boron trichloride lacks a complete octet. It needs electron. Ammonia donates its lone pair of electrons. BF3 accepts it. A coordinate covalent bond forms. no proton moved, yet an acid accepted electrons and a base donated electrons. The Lewis theory successfully explained reactions that neither Arrhenius nor Brønsted-Lowry could explain. Many students ask, which theory is correct? The answer is all three. Each theory explains chemistry at different levels. Think of them like increasingly powerful cameras. The Arrhenius theory gives a close-up view of aqueous solutions. The Brønsted-Lowry theory zooms out and explains proton transfer in many different environments. The Lewis theory gives the widest view, describing electron-pair interaction across an enormous range of chemical reactions. Each new theory didn't replace the previous one, it expanded our understanding. Now, let's compare them. Arrhenius theory: acid produces H3O plus in water, base produces OH minus in water. Strength: simple and practical. Limitation is that it works only in aqueous solution. Brønsted-Lowry theory: acid, proton donor, base, proton acceptor. Strength: it works with or without water, and the limitation is that still require proton transfer. What about Lewis theory? Acid is electron pair acceptor, base electron pair donor. Strength explains the wide variety of reactions. Limitation: because it is so broad, identifying Lewis acid and bases can sometimes require a deeper understanding of electron structure. Now let's revisit three reactions. Reaction 1: HCl plus H2O. Arrhenius: HCl increases H3O plus concentration. Brønsted-Lowry: HCl donates a proton to water. Lewis: water donates an electron pair to the proton from HCl forming H3O plus. Reaction 2: Arrhenius: not applicable because there is no aqueous solution. Brønsted: HCl donates proton H plus, Na3 accept H plus, that's proton. Lewis: Na3 donates its lone pair of electrons to the proton supplied by HCl. Reaction 3: BF3 plus Na3. Arrhenius cannot explain this. Brønsted-Lowry cannot explain because no proton is transferred. Lewis: perfect explanation. BF3 accepts an electron pair. Na3 donates an electron pair. Now listen to this. This theory are not just for examination. They help chemists design medicine, catalysts, fertilizers, industrial chemicals, polymers, and advanced materials. Understanding electron pair interaction is fundamental in coordination chemistry, organic chemistry, organometallic chemistry, catalysis, and material science. The evolution of acid-base theory reflects the evolution of chemistry itself, from simple observation in water to sophisticated explanation of molecular behavior. Now here are some high-yield examinations. If the question mentions hydrogen ions in water or hydroxide ion in water, think Arrhenius. If the question asks about proton donation or proton acceptance, think Brønsted-Lowry. If the reaction focuses on lone pairs, electron pair donation, coordinate covalent bond formation, think Lewis. A quick memory aid: Arrhenius equal to water, Brønsted-Lowry equal to protein H plus, Lewis equal to electron pair. And the simple sequence can help you identify the correct theory in seconds during an examination. Let's test your understanding. The comments answer these three questions. Which acid theory had the widest scope? Number 2, why can't the Arrhenius theory explain the reaction between ammonia gas and hydrogen chloride gas? Number 3, in the reaction BF3 plus Na3 to give F3BF combining with Na3, which substance is the Lewis acid and which is the Lewis base? Take a moment to think before reading other people's answer. Today you've seen how chemistry developed from one explanation to another, not because the earlier scientists were wrong, but because every new discovery revealed a broader picture of how matter behaves. Remember these three pillars. Arrhenius teaches us about acid and bases in aqueous solution. Brønsted-Lowry teaches us about the transfer of protons. Lewis teaches us about the transfer of electron pairs. Master this concept and you have a strong foundation for everything from secondary school chemistry to university level in organic chemistry. If this lesson helped you understand acid-based theories more clearly, please support this platform, this channel, by liking this video, sharing it with your classmates and every other person, and subscribing for more high-quality chemistry lessons. Follow me for more educational content. My name is Omotola. Fayomi.